Assalamu alaikum. Welcome to lecture number 8 of digital signal processing. In the last lecture, we have covered the sampling aspect of analog to digital conversion, and we concluded the point that technically speaking, sampling does not result in loss of information if the sampling rate is chosen carefully. But the quantization step always introduce distortion in the signal, and quantization is an irreversible process. After that, we have discussed some points regarding the sampling in detail. So in this lecture, we will continue from there and we will see that what are the problems arises due to the sampling. So here in this slide, we are going to see the sampling effect mathematically by using some mathematical expression and derive some conclusions with them. Initially, we have considered the two signals. The first one is a continuous time signal or analog signal, which can be represented by an expression xa of t is equal to a cos 2 pi ft plus theta as indicated by the pointer. And if we are assuming it as an everlasting signal, then the limit of t varies from minus infinity to plus infinity. Here f is the frequency of analog sinusoid or continuous time signal represented by capital F, and for our convenience we use different notations for the frequency of analog domain and discrete time domain. Here you can see that omega is represented by ohm for continuous time sinusoid, and we know that ohm is equal to 2 pi f. If you look at the expression of discrete time sinusoid, then you can see that expression is a cos omega n plus theta, where n varies from minus infinity to plus infinity, and here again omega is equal to 2 pi f. So by using this expression omega is equal to 2 pi f, you can expand the above expression and the expression becomes x of n is equal to a cos 2 pi f n plus theta. Here you can notice that we have used different notation for the frequency as well as the different notation for radian frequency. In continuous time sinusoid, we use the notation capital F if the frequency is measured in hertz, or notation omega is used if we want to note or calculate the frequency in radians per second. And for discrete time sinusoid, you can see that we use a small f to denote the frequency of that discrete time sinusoid, and for denoting its angular frequency we use the notation omega. So if we derive by using this notation, we are assured that we are talking about the discrete time domain or continuous time domain, as their notations are different. Now what we are trying to do, we are trying to establish some relationship between the frequency of analog signal, which means the frequency capital F of continuous time signal, and the frequency variable for discrete time domain, which is denoted by small f. So we are trying to develop some relationship between these two frequencies, that is frequency of the continuous time domain capital F, and second one is the frequency of discrete time domain denoted by small f. And in the previous lecture, recall that we already derived an expression t is equal to nt as far as uniform sampling is concerned. So this relationship is true, and we can also relate it to n over fs because we know that time is inversely proportional to the frequency. So if we have a continuous time sinusoid and we will apply uniform sampling on it to convert it into discrete time domain, then x of a becomes x of nt because the sampling interval is uniform. So we can replace x of t by x of nt in the expression. So here you can see that a cos 2 pi f capital F for analog signal and t is replaced by nt because we are doing sampling of this continuous time signal plus theta, which denotes the phase shift. Or we can say that t can be, or nt can be equate to, or just we can say t can be equate to 1 over fs because t is the sampling interval and fs is the sampling frequency. So here we are replacing capital T by 1 over fs because capital T is sampling time period or sampling interval and fs is the sampling frequency. So the expression becomes a cos 2 pi n f over fs plus theta. And if we want to compare it with the standard equation of discrete time sinusoid, which is written here, x of n is equal to a cos omega n plus theta, and you can replace omega by 2 pi f. So the expression becomes a cos 2 pi f plus theta. So this is the expression or generic expression of a discrete time sinusoid. We have studied in the previous lectures that any discrete time sinusoid can be represented by this equation. So this equation can be compared with the derived equation because we are doing sampling of a continuous signal, and after sampling, that continuous time signal is converted into discrete time domain. So we are comparing this expression with the standard expression of discrete time sinusoid. So after comparison, we can see that the small f in the discrete time sinusoid is equal to f over fs, capital F over fs, and we name it as a normalized frequency. So what is the normalized frequency? As the name indicate, it is the ratio between the two frequencies. First one is the frequency of the analog signal, which is represented by capital F, and the second one is the sampling frequency indicated by F over Fs. So we can also name this normalized frequency as relative frequency. So here small f is normalized frequency or relative frequency. And you know that for analog signal we usually measure the frequency in hertz, and the sampling frequency is measured in samples per second. So or hertz can be converted into cycles per second, because number of cycles per second is actually the frequency. So in numerator we have cycles per second, and in the denominator we have samples per second. So the unit of f, which is normalized frequency or relative frequency, becomes cycles per sample. Recall that we have already derived this unit in the previous lectures, but here we see in detail that how this relationship become true. So the unit of normalized frequency is cycles per sample, or alternatively we can say that omega is equal to ohm into T, because f can be replaced by T and we are just using the radian frequency. So in terms of radian frequency, this relationship becomes omega is equal to ohm into T, and T is the time period of the continuous time sinusoid. So concluding our discussion till yet, what we have understand that the frequency of the analog signal or continuous time signal can be related to the frequency of discrete time signal if we do the uniform sampling of that continuous time signal, and from that uniform sampling we obtain the discrete time signal. So now let's compare the range of frequency as we already studied for the continuous time sinusoid and discrete time sinusoid. In continuous time sinusoid, we already know that frequency range lie from minus infinity to plus infinity, and for discrete time sinusoid we know that the range or legitimate range for frequency is minus half to half. So using this important relation, which is the discrete time sinusoid frequency ranges from minus half to half, so replacing this normalized frequency factor by f over fs, then we will get this expression, which is indicated by the pointer. This normalized frequency is replaced by f over fs, and we will get this relationship, and relationship is the range of analog frequency minus fs by 2 to fs by 2, or in terms of the time period minus 1 over 2t is equal to 1 over 2t. This is the sampling interval, sampling period. So what we can reduce from this expression? This expression or relationship is very powerful in determining the correct sampling frequency to sample any continuous time signal and to convert it in discrete time domain. This relationship actually tells us that if we obtain a discrete time sinusoid by sampling a continuous time sinusoid, then at a certain frequency, we done the sampling at a particular sampling rate denoted by fs, then at that particular sampling rate we can have a particular value of f max. It means that when a continuous time signal is sampled at a particular rate, let's say fs, be generic at this stage. So when a signal is sampled at a particular rate, the highest frequency in present in a continuous time signal is f max, or simply f, that can be uniquely distinguished, which means that we have a limit, or this expression impose a limit, that if we will do sampling of a continuous time signal at a particular rate, then we have a certain range of frequency, and there is also a particular frequency denoted, or we can say it as f max, which can be uniquely distinguished. If we go beyond this range or beyond f max, then the frequencies present in the analog signal cannot be uniquely distinguishable. So this is the main problem which sampling can introduce in a signal, and this will occur if we do not follow or do not opt the correct sampling rate. And this expression also tells us the value of that maximum value of frequency of continuous time sinusoid that can be uniquely distinguishable. It must be equal to fs by 2, that is half of the sampling rate. Whatever the sampling rate we will choose, its half rate will be the f max. That is, this is the frequency which can be uniquely distinguishable in the continuous time signal. So what happens with the frequency beyond this range? So this is a very interesting discussion. I hope you are getting my point. And in the next slide we will learn more about this f max and this relationship, which is f max is equal to fs by 2, and we will try to answer the question that what happens with the frequency which lie beyond this range, that is f max, if it is present in a continuous time signal. In this slide we are going to discuss more about aliasing issue, which was discussed in the previous slide. Then we will propose some solution to overcome this aliasing issue. So in the last slide we have concluded that if we want to discretize our continuous time signal at a particular sampling rate, we must face some ambiguity regarding the uniquely distinguishable frequency belongs to the continuous time signal, and we denote that frequency with Fmax, and the value of that Fmax is equal to the half of the sampling rate. So here we can see with an example that we have two continuous time signals. First one is denoted by x1 of t, which is equal to cos 2 pi f10. F is selected as 10 and t into t, which is time. And for second signal we have selected f as 50. So these are the two sinusoids having different frequencies. Now we want to convert these two continuous time signals into discrete time domain. So for conversion, we need to sample these signals. Here we choose the sampling frequency as 40 Hz. I have highlighted the important figures with highlighter, so you may compare these numbers. The frequency present in the signal is 10, in the second signal it is 50, and we choose the sampling rate as 40. Recall the statement we stated in the previous slide that Fmax is equal to Fs by 2, that is maximum value of frequency which is uniquely distinguishable is Fs by 2. So here Fs is 40 and Fs by 2 is 20 Hz. So here, before solving or before using any mathematical expression or formula, we can comment that x1 can be sampled correctly without any loss of information if we choose this sampling rate. But what about the second signal, which is of 50 Hz and the sampling rate is 40 Hz? So what will happen with this signal? So we are going to learn this with some mathematical relationships. So see that we have used the relationship x1 of n, which is after sampling. When the signal is converted into discrete time domain, x of t is converted into x of n. X of n will become cos 2 pi small f, because we are dealing with the discrete time domain, which is the normalized frequency or relative frequency, which must be equal to capital F over Fs. And here capital F is 10. You may see the pointer, capital F and Fs, and this is the small f. So small f or normalized frequency or relative frequency is equal to capital F by Fs, 10 over 40 for the first signal and 50 over 40 for the second signal. So after cancelling the ratio, we will get cos 2 pi 10 over 40, n becomes cos pi over 2n, and the second signal becomes cos 5 pi by 2 into n. So what's the problem? Both the signals are successfully converted into discrete time domain. But if you look at the second signal carefully, then it is not the actual signal. How? Recall the second postulate of discrete time sinusoid. There we discussed that if the discrete time sinusoids are separated by 2 pi, I'm talking about their frequencies. If their frequencies are separated by 2 pi or integer multiple of 2 pi, then both the signals will be the same. So the same is going to happen with this second signal cos 5 pi by 2 into n. We can represent this 5 by 2 with 2 pi n plus n pi by 2. And here you can see we have a factor of 2 pi n, which is the statement of the second postulate that our frequency is separated by integer multiple of 2 pi. So we can ignore this 2 pi n. What we will get? Cos pi n by 2 or cos n pi by 2, which is we obtained from the first signal also. So both the signals gives us the same result. However, the second signal is different, having some different frequency. But when we discretize it by using the sampling rate of 40 Hz, this signal will overlap or look like the first signal. So here we can comment or we can state this second signal as an aliased version of the first signal at a frequency of or at a sampling frequency of 40 Hz. So if we choose some other sampling rate, then the scenario will be different. But if we select the fs as 40 Hz, so in this case the second signal is the aliased version of first signal. You can also see that I concluded with the remarks that x2 of n is equal to x1 of n. We will get the same samples or same sequence. However, we know that the continuous time signals are different in the continuous time domain. Both the signals are different in shape, having different frequency. But what we are getting in the discrete time domain, we are getting the same samples or same sequence for both the signals. So when we want to reconstruct these signals again into continuous time domain, we can't do it for the second signal. We are able to convert or reconstruct the first signal properly, but second signal cannot be reconstructed properly, as this second signal is the aliased version of the first signal. And our discussion is not limited to this point. This is not the only aliased version of first signal. At this particular rate of sampling, which is chosen to be 40 Hz in this case, we can also have other aliases of this frequency. For example, if we take this continuous time signal having the frequency of 90 Hz, again we will get the same signal as we are getting x1 of n. Not only f3 as 90, if we select frequency as 130, we will get again the same signal, and this series will continue. So we came to know that not only a single frequency can be a aliased version of one frequency. There must be multiple frequencies which can be the aliased version of one frequency at a particular sampling rate. Recall that, remember this statement that at a particular sampling rate, if we change the sampling rate, then the alias frequency becomes different. But at a particular sampling rate, we will have unlimited aliased frequency for a particular frequency. So what will be these alias frequency for a particular frequency? We need to know the relationship between these two terms. So here is the relationship indicated by the highlighter. Please see the pointer. Fk is equal to f0 plus kfs. Fs is the sampling frequency. So for a particular sampling frequency, k is an integer, and k can vary from -infinity to +infinity, and f0 is the fundamental frequency for which we are trying to determine the its aliased version, and fk is the aliased version. So let's try to map this formula on the example we discussed. If f0 which is the fundamental frequency is 10, k1 for the first aliased version, and fs is selected as 40, then 10 plus 40 is 60, 10 plus 40 is 50. So fk is the 50, which is the first aliased version of 10 Hz frequency, which is also proved from the mathematical expression we have discussed just before. If we want to determine the second aliased version, change k from 1 to 2, then 2 into 40 is 80, 80 plus 10 is 90. When k is 3, 3 into 40, 120 plus 10 is 130, and the series will go on. So this is the problem which can arise in the sampling process named as aliasing, and it will occur if we not properly select the correct sampling rate for a particular signal. Let's assume another example. We have proved our concept mathematically by using a mathematical equation. However, we can also use the plots of these expressions. So in the second example, we are going to prove this concept with the help of sinusoidal plots. You can see in the slide that you have a plot in which two sinusoids are overlapped. The first sinusoid is having the frequency as indicated in figure. f1 is equal to -7/8 Hz. So this sinusoid is varying with this rate, and we assume another sinusoid having the frequency of +1/8. So these are the two unique signals because they are having the unique value of frequency. Now we are trying to discretize these signals. So discretizing involves the sampling. So we are actually sampling these two signals. So in this sampling procedure, we have to select some sampling rate, and we have selected the sampling rate as 1 Hertz. Here it is mentioned that fs is equal to 1 Hertz. It means after 1 second we have to take the sample of that signal. So you can see that we take the first sample at 0 second, the next sample will be at 1 second. You can see the pointer at time t is equal to 1 second. We take the second sample at time is equal to 2 second. We take this third sample, and so on. We take the several samples of these two signals at a different time instant, which is uniformly distributed, because we are discussing the uniform sampling. So very interesting thing you can note from these two plots, that both these signals will give the same sample values or sequence, because what will happen, we will only have these sample values or sequence in discrete time domain. We will have a set of values such as x of n is equal to 1, 2, 1, 3, 4, and so on. We do not have any idea about the shape of these analog signals. We can imagine that if we have these samples and we will try to reconstruct an analog signal, then usually we can apply the interpolation. So just see that the first sample is this, second sample is this, and third sample is this, and so on. So if we apply the interpolation, then we will connect the first sample with the second sample, and second with the third, and third with the fourth. So we will get the shape close to this signal, which is having the frequency of 1 over 8. But we will never get the signal which is having the frequency of minus 7 over 8. So it means that this first signal, which is having the frequency of minus 7 over 8, is actually the aliased version of second signal, which is having the frequency of 1 over 8. You can also prove this mathematically as we did with the previous example. So you will come up with the result that if you have a frequency selected f0 as 1 over 8, then minus 7 over 8 will be the aliased version of 1 over 8. And you can also see from the plot then that we are able to reconstruct the original signal if the frequency is 1 over 8, and if we select the frequency as minus 7 over 8, we are unable to reconstruct the original signal. And this is actually the sampling why we are sampling this signal, because we want to convert this signal into discrete time domain, and after once the signal is discretized, we will apply some algorithms or intelligent processing techniques to extract the meaningful information. And if the information is lost at this stage, which is sampling, then no need or no benefit of doing any signal processing, because we already lose the information at the first stage, which is sampling. So I hope that you all get the idea how important the sampling is and how carefully we have to do sampling, what's the significance of sampling rate, and if we do not follow the sampling criteria, then there is no need to do signal processing, because we already lose the information in the sampling stage.